Okay, good morning, everybody. This is the last class that we have, not only for AE 3140, but also for your entire study abroad program. It's been a 10-week journey, but I'm sure there have been ups and downs. But whatever it is, I think you would have hopefully enjoyed the learning process as much as I did learning to make you learn. So this is the final class. Initially, I had plans of continuing the review, but I thought I'd just share the slide deck with you. And if necessary, you can always get in touch with me and we can always catch up on Teams or something if you need any clarifications or anything. Because as I said, we've covered everything that needed to be covered in this course, but just that we wanted to get into some of the details and nitty-gritties, but I think we've done enough of it in the last Thursday's class where we reviewed in great detail the applications to beams. So before you get on to your grand finale, so to speak, I would like to see if you have any questions related to structural analysis overall, including questions related to what you're going to present today. So if there is anything that I can address, I'll be happy to do so, so that then you can go ahead and wind it up. Feel free, anything that you might want to know in whatever we have done, or what you think what structural analysis is, or anything related to your deformable bodies, or where you go from here if some of you would like to take a few more structures related courses in the future, anything related to that. Yeah, maybe I can.
Just for this project and in general, I saw a lot about stress tensors and stress functions as well. So is that something that we can expect in the future?
So that's a very good question. So if you're looking at in terms of understanding structures from a very, very basic generic perspective, also from the point of view of research, etc., then the tensors are the best way to go. But if you're looking at more from an engineering point of view, just implementing for some practical problems, mostly involving numerics, etc., all of this is kind of within a black box in most of the software, and you really don't need to kind of enter into the tensor analysis. But tensors not useful not only for structural analysis, as you might know, it's a mathematical tool that can be of great significance for many, many other courses and other parts of learning as well. So if you have an inclination towards it, it's good that you go ahead. Most people get overburdened or scared of it upfront because the way tensors are introduced mostly from mathematicians' perspective, whereas the way we engineers utilize it is very, very different. So there are some really great online tools as well for understanding tensor analysis from an engineer's perspective. So I'll try to share some references related to that, and you can see if you can go from there. And though this course might be over, I'm always available to you whenever you need to catch up on anything, especially related to structures and or math, tools related to structures, etc. Feel free to ping me, and we can always catch up on that. Yeah. Thank you. Anybody else? Anything else? Okay. So maybe after you present, maybe we can. If you have any questions or you think about something, we can continue on this. Yeah, you can go ahead, set up your presentation. There's this table. Yeah, pull it.
Okay.
I sent the PDF entire document.
Okay. Alrighty.
This is the PDF, right? Maybe you can see if you can make it full screen.
Uh, I don't know.
Because there's a lot of content, so how much more space we can utilize, the better.
No, let's put to page. Actually, don't know.
Present.
I mean, I think.
There's an option to present there.
Okay. Okay.
There you go.
Cool.
You can zoom in.
Yeah, we'll zoom in. Okay, so this is our overall variable chart connecting different variables between loads, stresses, deformations, strains, and connecting those via equations like the constitutive laws and equilibrium equations. So let's see.
Go over our legend first.
Yes, yeah. I don't know. It's hard to. I can't really zoom in presentation mode. Yeah. So, over here, just to go over our map, we have our legend. So, over here, this is our system, aka like just different like scenarios in which these variables could be used in, such as an axial beam or a torque problem, or like through different scenarios and systems like that. Loads are defined by the red ovals. Equilibrium equations are defined through the orange. Stresses are defined through yellow. Constitutive law is between the green. Strains are blue, well, light blue. Kinematic equations are dark blue. And the deformations can be seen with the purple. And between all of these systems, you have, between all of these types of variables, you have equilibrium equations being related to with each other with loads and stresses. The constitutive law connects the stresses and the strains, while the kinematic equations connect the strains and the deformation. Does anyone want to go?
So we all saw your email about the patterns to look for in this. So the pattern we decided to go with was using what we have as our legend as just a guideline of a pathway to step through certain systems and certain problems. So you can see here that we have a couple different systems. There are more, but these are just the ones that we focused on. And the way that it leads from loads all the way down to deformation. And sometimes the arrows do overlap and intersect, but that is the nature of these systems, that they often work in tandem with each other, especially other principles.
Yeah, so I suppose we can just go into like the specific systems that we want to do. So do you want to zoom in on axial bar? Okay, so for axial bar, we have three different forces that could be acted on that we chose to focus on based off of our variable chart that we did earlier. So the main two here are tensile and compressive forces. And so those lead into our equilibrium equations. Right here, this F equals, or force equals the area multiplied by our stress that connects our tensile force to our axial stress. And then to connect our axial stress to our axial strain, we have Hooke's law, and there's the normal stress divided by our Young's modulus, which equals our axial strain. Then our kinematic equation finally connects our strain to our deflection. It's just the derivative with respect to x of our axial strain. And we also chose to.
By M?
Sorry, that's the units. So in meters, the SI unit. Yeah, obviously that could be inches, feet, whatever, but we just chose to do SI units. Yeah. We also had body force up there. Body force is very general. It could, apply to gravity, magnetic force, electrostatic force in general. But we just added that to the axial bar section. And this is sort of a general equation relating to our sigma value, our stress value. So yeah, that's the axial bar section.
I would also like to add, for compressive force, that between compressive force and tensile force, there's different types of deformations that can happen. So for compressive force, particularly, if you're compressing a beam, there can be a chance for buckling. So that could be covered by this U value as well. And there could also be, and within the tensile, just pulling tension of the axial bar, you probably see an extension or an elongation of the material. So from there, we can go into different types of springs. And a lot of it actually, there was a lot of overlap between how the axial bar and springs were acting on a material. So though we have tensile force and compressive force over here, right? For mechanical spring, we also have the same tensile force and compressive force where the spring is being pulled or it's being pressed down. And that can be related by a different form of Hooke's law as well, where we have the K value for, we have force is equal to K times dx. And from there, force is equal, so for tensile force, that would be that would be relating K times dx is equal to F. And that would be relating both these loads and the deformation as well. From a this doesn't quite make sense.
It looks like you have a few repetitions.
Yeah.
I think,
Yeah.
the equilibrium equation and the constitutive law getting
Yeah.
interchanged.
Yeah.
Yeah, just one thing to add to that. So we have the block with F equals negative K dx coming from both tensile force and compressive force on both branches. And this was just a way to differentiate that there are tensile and compressive forces, but they do ultimately come from the same mathematical formula.
Before we move on, probably one more thing to distinguish between the tension and the compression is in terms of what is important from a geometric point of view. Because from the material point of view, already you know that the Young's modulus is what is going to be the primary driving factor there. So you want to have better performance either in tension or compression, you go for a material with larger Young's modulus. But if you're looking at, let's say, from a geometric point of view, what you'd like to have as a solution, there's a very subtle difference that we discussed in class about what compression? What is the geometric factor important there? What's the axial bar stiffness given by? How do you relate? See, eventually the end goal is to relate your loads to the deformation by bringing in combining all three sets of equations, right? So you recollect how F and U are related. So that U that you had in meters and the F that you have in newtons, how are they related to each other? What is the
Through like Newton's law and like F equals mass times acceleration, which is the second derivative of displacement.
Yeah, that's getting into dynamics, but right now, even before you get there, there is much more subtler ways. See, you've gone in three steps, right? So you've gone from the force to the stress, you have introduced the area, right? So then you've gone from the stress to the strain, you introduce the X modulus E, right? So then you went from the strain to the displacement. It's a derivative, dou U by dou X. Okay, so the way those two are related is through the axial stiffness EA. Right? So just like you can make it perform better in axial tension by changing the material to larger Young's modulus, you can also do the same thing by going to a bar made of the same material but with a larger cross-sectional area. Right? So that's how you improve it in tension. But if you want to improve it in compression, there's something more that you have to do. One is, yes, area can again be a solution, but only up to a point, because beyond that there's also a possibility of buckling. Okay, so when buckling comes in, the moment of inertia I or the torsion constant J become important depending upon whether it will be flexural buckling or torsional buckling that will happen. So to cut the long story short, qualitatively what we are saying is that one is you can improve it by changing the material. One other thing is by improving the geometry. And when you're making the geometry choice, there are always two things, size and shape. Okay? In tension, only size matters, cross-sectional area matters. In shape, the shape doesn't matter. Whereas in compression, both the size and the shape equally matter. Shape comes into picture if buckling is a concern. So these are the subtle things that I want you to kind of keep in mind as you go forward. It's not necessary for all of that to be on the chart, because the chart is more of a pictorial mnemonic for us. But over and above that, if you imprint in your mind, when you see those different connections, you see what eventually they are leading to. That's important, because the same thing what applies to the bar applies to the spring as well, the tension spring in particular. So there are a few corrections that you can make when you go back. So not from the point of view of giving it to me, but from the point of view of it being a pedagogic tool for all of you for the future. It will help because you see that KDX appearing twice. That's not appropriate. So there's something wrong with that. So you see what are the two things it connects. So I really like the way you've brought in the color theory and the different shapes to this. It kind of distinguishes the variables from the equations. But at the same time, be very, very careful what two you're connecting. Are those two figuring that equation you have over there? For example, here, when you're connecting these two, it's very clear that both sigma and epsilon are there. And there's some connecting factor, which is what Hooke's law contributes. But when you're connecting something else over here, obviously this has to connect. See, if there's an arrow going there and an arrow coming here, these two arrows indicate that it's these two things that this box is connecting, right? So then obviously it has to have an F1, which it does, but it should also have a sigma instead it's having a dx. So there's something wrong with that, right? So what it really should be is F is equal to area times sigma xx. Okay? So something like that. It's just pictorially you can see those balloons, the circular ones, are the variables, and the square or rectangles are the equations connecting them. So every one of the boxes which connect two circles has to have those two variables in it. Okay? So if that's a test for you to see if things are going right or they're not going right. For example, if you're looking at these two, it has an epsilon on one side and it has the x on the other side. Okay? So, and be consistent with the units. So X is usually you have it as a coordinate system measure, whereas what he used there over there, I think U is the more appropriate thing, U as a function of X. So on the same chart, if you use more variables, already there are too many things happening, it's a busy chart. And if you use for the same quantity two different notations, you only are going to confuse yourselves. Okay? So just make things as simple as possible so that it becomes a learning tool for you.
So I guess we can go on to the next one. Oh, did we? Okay. Torsion, basically the same idea as the mechanical spring, except the displacements in like the x direction or whatever linear direction is replaced with a radial position. So for the equilibrium law, we have negative k times d theta, and we'll have to relate that similar to with the spring to tau xx. But then from tau xx, we use Hooke's law to relate that to the strain, and then from strain, we relate that to the displacement of theta. And then we also have heating / cooling. And for this equation, we basically introduce the coefficient of thermal expansion. So we still have F equals A times sigma, but sigma in this case can be replaced by E, coefficient of thermal expansion alpha, and delta T, the change in temperature. And then from sigma, we once again use Hooke's law to find the thermal strain, which is represented by alpha delta T. And then from the thermal strain, we can find the change in length of the beam, and then find the, I guess, overall change or deformation.
Just because it's really well done, there are no issues with this flow. So you see what I was trying to explain with the other things, that all of those things are taken care of over here. So what two things you're connecting, and what is the new material property or new geometric feature which comes in. So this is precisely what will really help you to look at the big picture, and when there are more subtle questions, more involved questions, and especially you doing research, having that bigger picture will make you move towards your focus area very quickly and efficiently. So that really helps. That's good.
Okay, so another topic for us was drag or fluid resistance, which involves in the viscous force. And since we were focusing on drag, this is typically expressed with a negative sign because it's opposing the direction of motion. And so what we have here is relating our force, which is equal to our viscosity multiplied by area. And this also relates to our area multiplied by our stress as well. And going from stress, we can again connect stress to strain via Hooke's law. But for viscous flow, the stress is actually proportional to the derivative of strain. And so our, our constitutive law is our stress is equal to the viscosity multiplied by E dot or the or epsilon dot, or the rate of change of strain. And so once you have the rate of change of strain, you can again take the second derivative. It would be a second order derivative of our deflection, but it would be first with respect to dx, but then with respect to time as well, to get to our deflection in meters.
I really love this example as well because it gets into a different kind of physics from solid mechanics to fluid mechanics, but still shows that the same overall picture works. So, and also by taking into account the rates of change, because fluids cannot hold their shape and size, so essentially you have to make sure that the rates come into picture. So that's where your d by dt terms come in. Just one point you have to be careful about the Hooke's law when you use. With the normal stress and normal strain, that's when your Young's modulus comes in. Otherwise, it's a shear modulus.
Right, yeah.
But in any case, this is not something applicable here. This is where you eventually end up with.
Yeah.
So that's fine.
Okay. Yeah, this is sort of relating to dynamics in a bit, but yeah, it was an example that I used.
Yeah.
Sure, yeah.
So for flexural beams, we're going to be looking at different like moments that are happening to the beam itself. So there's a force, and there's creating like a moment to the beam. So the loads we have are bending moment counterclockwise, bending moment clockwise, and this moment can be related to the stress via the moment equation, which is that m is equal to a times the stress. And then from there, we can see how we can relate the stress to the strain, once again via Hooke's law. But I believe this would be more of like a shear strain, no?
The shear effects will be there, but it's
Yeah.
very minimal, and
Okay.
I showed already that it's negligible.
Okay,
And
okay.
some of the homeworks that you showed in last class also, you were showing that tau max by sigma max is a very small number.
Oh, okay, okay, gotcha.
It's not important, but you have to be careful when you do this, because this is something that is valid when you have a uniform sigma throughout. But
Yeah.
here you don't have a uniform sigma throughout. Sigma varies linearly, as you showed in the previous class. So the relationship between m and the sigma is a little more complex.
Okay.
So it typically will be a linear function of x. But also you have to be very careful in which variable you use, because the x that you're using is also associated with a length.
Yeah.
So what we are talking about there is the distance from the neutral axis, which is y.
Okay.
So, and the A that you have is not the actual area of the cross section, but dA, the differential area, and then that is integrated over the cross section.
Okay.
So this is not appropriate, but I guess you see where we are
Yes.
heading towards.
Yeah. And you know,
Also, this is also not the appropriate equation to use, because the primary deformation that is coming because of a moment is not axial
Yeah.
displacement, but it's the transverse displacement,
Yeah.
not u1 but u2.
You too.
And that it's the second derivative which will come into picture, multiplied by the moment down. So we did all this in class last time, so if you can just go through the video or the slides, you'll see that it's much more involved.
Yeah. Okay. And then lastly, we have torsional beams.
So for our torsional beam here, we have the two forces, the shear force and the compressive force, that will come into play. And we have our equations, we relate Hooke's law, and here we actually did get it right with using the shear modulus instead of the Young's modulus. And yeah, our equation F equals A star Y, A times Y11. And this can be related through the shear 1,1 in the matrix. And yeah, ultimately, through Hooke's law and through our equations, we have to use a derivative down low, but we can relate this back from our radians, our degrees, back to the torsional beam to find the angular deflection.
Again, this is absolutely inappropriate, because torsional beam, the main load, as you know, is the torque.
Yeah.
So the shear force is something that will come in the bending problem, not in here. Here you will have the shear stress which will be coming because of the torsion, but the torque is the main thing, and what you will have to be relating here is the torque to the shear stress. And just like I was telling Nilesh, that you have to look at an integration over the cross section. Similarly, you will have an integration over the cross section of that shear stress to lead to your torque. So forces are not there. So over here, and again, as far as this is concerned, yes, this is a correction you made from the previous one. And also, yeah, you need to be a little more precise in how you define these things. This is correct equations, but what do they mean and how they are related to that will come in only if your starting point is right. So if the starting point itself is messed up, then you're going to have an issue there. So change this to torques and then use the appropriate equation here relating to the taus, because that equation should have both the tau as well as the torque, and then you will see where you're heading. Again, this is something that we have done in class, so just have to revisit that, those slides. Just a single slide has all of that information on the top, you just have to grasp it from that.
Yeah, so those were, I believe those were all of the examples that we were going through. So, yeah, if there's any other questions or any other corrections we need to make.
Yeah, so you brought in that analogy between the axial bar and the mechanical spring.
Yes.
So similarly, you have an analogy between the torsional, you can call it a torsional shaft or a torsional beam, but that and the torsional spring. Okay. So once you correct all of those variables and also the equations connecting them, keep in mind that the variable should be an appropriate variable for that particular body, and then you have to make sure that the equations, as I said, the box always has the two balloons which are connecting it, whatever variables they are there, they have to figure in that box, otherwise it doesn't make sense that they are connecting them. So that's what the equation essentially means. They're essentially connecting two sets of variables. You probably know one set and you want to determine the other set. That's when you use the equation, right? So that if you stop by, first of all, start from whatever the system is, and then see what are the appropriate variables associated with the system. In all the cases, you're starting with the load. So it's very clear, axial bar, you should have a tension or a compression load, a force. Similarly, if it's a torsional spring, it has to have a moment. Similarly, torsional beam, you have to have a torque, right? So similarly, if it's a mechanical spring, very similar to this. And these are very interesting problems that you brought out, brings in different physics, so it gives you the idea that pretty much everything in physics can actually fit into this overall big picture. Once you start looking at it from this perception, what seems complicated in details, you can actually see is actually quite simple. It's more of terminology that you're getting bogged down with. And then once you see that bigger picture, connecting the dots becomes easy. That's it.
Yes.
You are planning to redo some of the other.
Oh, yeah, you guys did? Okay, okay. Is it on the drive?
So upload these files to the team as well.
Yes, yes.
Your contacts on it.
Okay. So who wants to?
Okay, so here's the redone proof for C44 and its relations within the C matrix and to the shear list. So we start off with a regular body that is being deflected, and I redrew it down there just so it's a little easier to visualize the different values, like the different torques that go the different shears that go in, the deflection values of delta x1 and delta x2. And yeah, so then that one we
You
saw.
need to move around and show what you're.
Yeah,
There's a lot of
it's
information.
it's all the way
So
up there
exactly
though.
Talk about it. You can use the mouse. Exactly. To show exactly what you're talking about.
Okay, so we have here just the basic body that is undergoing some shear stresses that leads to it being deflected, and we can see here that some of the angles are elongated and some are compressed, and we can use this to help us determine more of the properties in this better free body diagram down here. And we have to use the compatibility matrix along with constitutive law, to solve for this. So I have the equal signs in here to show the relationships that we solve for in class. And to solve for the property that we want, which is C44, we'll just keep everything as 0 and only look at tau 1, 2. So this is the only property that's not equal to 0. It just makes it easier for analysis. Oh, I clicked something. And here, this section up here was proven in class, but we're looking to prove this section down here. So we can do that by looking at the relationship between gamma 1, 2, C44, and tau 1, 2, which is shown here. I use C because the C matrix is the inverse of the S matrix. And here, I'm trying to figure out what I wrote here. Yeah, x1, x2 plane. So yeah, this is what we're looking at here when we say the subscripts as x1, x2 are the x1 and x2 planes here. So we can look at the shear modulus here with, that's not supposed to be 4, 4, that's supposed to be 1, 2. But yeah, and then that over gamma 4, 4 can ultimately get us to this relationship here because these cancel out, that C44 equals 1 over the shear modulus. And based on the matrix identities that we showed in the previous classes, that would also mean that C55 and C66 are also 1 over the shear modulus. So going over here, we can see that the Young's modulus, we can use this to relate to the form that we actually want to get to, which relates the shear modulus, the Young's modulus, and the Poisson's ratio. And in this one, it was a smaller case to consider where sigma 1, 1 was not equal to 0, which was identical to what we did in class the other day. And C23 is the negative Poisson ratio over the Young's modulus, which is also shown. And we can use these to substitute in the values. Here's the relationship, and then ultimately get our final form here.
I don't think we are getting where we want to, because it's a very, very clearly stated problem. You just want to prove that C44 is equal to this, of course, the inverse of that. So you're having S. When you invert this matrix, you have C44 here, right?
Mm-hmm.
So you want to prove that C44 is C22 minus C23 divided by 2. So if you want to do that, you just have to get into the physicality of what C44 means, what C22 means, what C23 means. None of these are actually required. All of these are things that we already did in class. What we want is the next step. We only want to prove, we don't even need a matrix. We only need this quantity here, and this quantity here in the inverse matrix. Not the same S's, but the C's. Okay? So you see what C44 means. C44 has nothing to do with tau 1, 2. It's essentially connecting your tau 2, 3. Okay? It's connecting your tau 2, 3 to your gamma 2, 3. And the 4, 4, 5, 5, 6, 6 notation has no meaning here. These are actually shear strains, the last 3. And all of them should be twice the engineering shear strains. And you should have 2, 3, 3, 1, and 1, 2 over here. Right? And so you take one by each one of them, tau 2, 3 versus gamma 2, 3. What is the relationship? what is the connection between C22, C23 and the variables involved. Then you do exactly what Nilesh did in the previous class to draw this picture. And from this picture, you get to showcasing two different aspects. One is in the XY plane, where you have the shear stresses, and then at 45 degrees to it, where you have the tension and decompression. Now, the shear in this XY coordinate system will essentially relate your, will bring your C44 into picture. For the same problem, you're doing a coordinate transformation, getting your other two stresses, because in this direction it's getting pulled, in this direction it's getting compressed, which is equivalent to this shear that you have. Then you will bring in C22 and C23, and then you can connect these two, and then you come to the derivation. So this is just repeating what we did in class, which is not at all what we want. We want just only that proof of C44 is equal to C22 minus C23 divided by 2. So just try to take a look at, if you're interested, you can just email that to me, and then I'll see if you're going in the right direction.
Okay, yeah, I think.
Did you understand what it is?
Yeah, I do. I understand. I know that I noticed that mistake up there too. That
All
was
you
just a
needed to do
copy.
is to just look at what Nilesh showed last time. So just, if you, I think she still has that slide. Yeah, so if you look at the slides, it's exactly these two pictures all that you need. Just the only difference between what has been done by Nilesh, what needs to be done by you, is instead of the E's and G's, you now have your C44s and C22 and C23. So that's the only difference, okay? So just make sure you follow, sit with Nilesh and try to understand this process. If you understand this process, then all that you need to do is to correlate between what is the difference between G on the one hand and your C44 on the other hand. What is the difference between your C22 and your E on the other hand? And what's the difference between C23 and the Poisson's ratio mu on the other hand? Once you correlate these, exact same process. You just have to substitute those different variables and get it back.
Okay, yeah, I think I also may have written down the problem wrong during class because I wrote down that I should derive this equation and relate it back to C44. So I kind of did the opposite thinking process where I was working backwards instead of forwards.
So this is a redone version of the shear stress over the normal stress for an elliptic cross section. We defined our x and y axis up there, and a is the length of horizontal is the horizontal length, and b is the vertical length. So first off, I started with deriving sigma max. I just noted that the equation for the ellipse, just for boundary, for like our boundary conditions, it's our x over a squared plus y over b squared equals 1. And so first I started off with deriving the second moment of inertia. So I started with first taking the moment of inertia about the x-axis, and that's equal to the integral of x squared dA. And doing that, we get, you would have to do a double integral, but we can see that it ends up being 1/4 pi a to the third times b, which is kind of analogous to what it would be if it was a circular cross-section, except it would just be your radius to the 4th power. And then I just factored out pi ab in that case because that's the area of the cross-section. And then a similar process for the moment of inertia around the y-axis. Take the integral of y squared dA, and again factor out pi ab. And then our second moment of area equals our two moment of inertia around our axis added up. And what we get is our second moment of area is equal to 1/4 pi ab multiplied by a squared plus b squared. From there, I looked at deriving the relation between sigma, or sorry, sigma and our moment, as well as using our second moment of area. So first, this is just from the definition of strain. I guess, so here would be A prime B prime minus C prime D prime, and that's just the final positions after the bending has occurred over C prime D prime. And then relating that to, in terms of R and theta, which is the angle and the radius, it would be R plus B theta, or sorry, R plus Y theta, which is the distance between these two lines, minus R theta over R theta. If we distribute this over, we see that the R thetas on the numerator cancel, and we get a Y theta over R theta, which just simplifies down to Y over R is equal to our strain. Then using Hooke's law to tie it back to our stress, we get the relation that the stress is equal to our Young's modulus multiplied by y over our radius. And then also over here, I just added that a force is equal to our stress times our area, so we can substitute this expression over here. And relating it back, if we multiply both sides by y, we get our y squared a term, which we can sort of factor out and relate it to our second moment of area. And so rearranging this equation, if we, right, yeah, so if, since our, once we get this, we can relate it to our, by combining both equations, sigma over y is equal to our moment divided by our second moment of area. And this just relates, just multiplying both sides by y, we get that sigma equals our moment multiplied by y over our second moment of area. And in order to maximize sigma, we need the largest possible value of y, which would be a in this case, and dividing that by what we found up above, we see that our a's cancel, so we get a final expression for sigma max is equal to our moment multiplied by 4 over pi times b multiplied by a squared plus b squared.
It's a kind of a mixed bag here. So what you have done with the bending is more or less okay, and to reach to your sigma max. No issues except that you would have the second moment of area rather than the j over here. Okay, so depending upon about which axis it's bending, you would have either ix or iy over there, right? So iz or iy if x is along the line. Okay, so that's just the one mistake, but more or less this is quite all right. But the torsion you'll have to completely revisit, because remember we've been stressing time and again that the torsion constant is different from the polar moment of inertia for all cross sections except circular, and this is not a circular cross section, it's elliptic. Even if elliptic in a special case of A equal to B gets to a circular, still this is J is not given by the torsion constant. So you have to actually determine J from a more fundamental first principles. It's good that you wrote on the ellipse equation, it's good that you calculated the I's, etc. But those are, the I's are not going to be of relevance over here. Okay, what is of relevance is to go to a similar kind of a workout as far as torsion is concerned. So So all that you do is you're applying the torque. When you're applying the torque, it's twisting, right? So when it's twisting, what happens? What are the stresses that are generated? How are they counterbalanced by the torque? And how that in turn correlates with the twist angle and the movement of the, let's say, area element in the circumferential direction. So all of that you have to do in the same manner with that to get to your tau max. Then only you'll be able to compare these two. Okay. So your J, always remember this. I think I mentioned last time also when you and a few others presented that J is called the torsion constant. It just happens to be by fluke the polar moment of inertia for a circular cross section, whether solid or hollow. Okay, but never ever think of it as a polar moment of inertia in general. Okay? It's just a coincidence that it happened for a circular cross section that they are the same. And the equations that you use to determine that are very, very different. Okay? So, yeah, for example, last class we showed that arbitrary shaped thin walled cross section where it just became 1/3 the length times the thickness Q. Okay? That's how you determine it. And that has absolutely no correlation with the polar moment of inertia of that. So, depending upon whether it's a thin open section or closed section, if it's thin walls, or a solid cross section like this, you have to determine it from first principles. Okay, and these may or may not come in handy for you in that derivation. What will come in handy for you is just to follow this in a parallel process. Okay? There are quite a few textbooks which will showcase this. You can look through some examples for that. May or may not give you specifically for an elliptic cross section, but whatever a non-circular cross section they give for, the methodology remains the same. As long as you understand for one, the process remains the same for the others as well. Okay? It's just that when this becomes a special case A equal to B, then whatever you have done holds. But once A is not equal to B, you will have a different approach on these lines. Okay? From first principles. Go to the displacement, go to the load that is applied, how is it resisted by the stress, and then you have to connect all of them together to eventually reach your tau max. That's the path. There's the other special case where B becomes very small compared to A, then it becomes just like a thin strip. Okay? So then your 1/3 length times thickness cube will become applicable. So in other words, if B is very small compared to A, it just becomes your 1/3 of A times B cube. That will be your value of J. Again, has absolutely nothing to do with the polar moment of inertia, right? So keep that in mind. The other thing is, a lot of people, I don't blame you, but even textbooks call this as inertia just because the notation I is used, but this has nothing to do with inertia, which you would have learned in dynamics, which is integral of length squared times dm. So that's how you get to the moments of inertia. This is the moment of area, because the area is what you're taking the moment, and it's the second moment of area. I know you actually corrected your expression of that as you went on, but initially you started calling that as inertia, which is a legacy of unfortunate terminology used by a lot of books as well. So just be aware of that.
Okay. All right. Thank you. For tau max, I.
Oh no, sorry. I jumped in the wagon. So you should have told me that you have this.
Sorry. For tau max, I used a Prandtl's stress function, which relates tau 1. By the way, tau 1/2 is the shear stress over the y-axis, and tau 1/3 here is defined as the shear stress about the x-axis. And so how he defines it is tau 1/2 is equal to the partial derivative of his stress function over dou y, and then he defines tau 1/3 as the negative partial derivative of his stress function with respect to the x. And then his actual stress function here is it's equal to negative m over a, and then in brackets, it's when the boundary condition, like equation, so basically the equation of the cross-section is equal to 0. So what I did was I inputted the area, and also I set the previous cross-section equation to 0, so that's where the -1 comes from. And then from there, I evaluated the partial derivative of that function. And so the partial derivative with respect to y, this becomes 0, and the 1 also becomes 0. So you're only evaluating this term over here, and obviously multiplying it by m over pi ab. And so what you end up getting is negative 2m y over pi ab. It should be to the third power. It's a little unclear, sorry. But that should be to the third power. And then tau 1,3, you follow a similar process. It's just that the second term and third term go to 0, and you're only evaluating this term. And so what you end up getting is 2 times the moment multiplied by x over pi a to the third times b. And then the max shear stress for each axis happens at their respective extreme points. So for tau 1,2, that would be when y is equal to b. And so if you substitute in b, the b's kind of cancel out, and you're left with tau 1,2 is equal to negative 2m over pi ab squared. And then similarly for tau 1,3, you input it when x is equal to a, and so you end up with 2m over pi a squared b, because the a's cancel out. And then you want this denominator to be as small as possible. And since a is the term being squared here, this fraction here would be larger than this fraction, just by how we've defined a and b. And so what we end up with here is that tau max is equal to 2m over pi ab squared. And then I took sigma max from the previous slide and just divided the two expressions that we derived. And from there, I found that tau max over sigma max is equal to a squared plus b squared over 2ab.
Keep giving me pleasant surprises like this. I love it.
Okay, so this is the tau max flange and tau max web derivation for a T-section beam. So we have to start off by making a couple of assumptions by saying that the beam is subject to it's pure bending, it's isotropic, and it obeys Hooke's law. So those assumptions will allow us to go further in the analysis. I drew out a diagram of what the terms will be called between.
If you have pure bending, you'd have axial stress, you have shear stresses at all. So pure bending is when you have on both sides of the beam, you're having only a moment, right? So no forces. See, both a transverse force as well as a moment can cause this to bend. Okay? So tau will happen if and only if in an isotropic material, at least it will happen only if and only if you have force, transverse force. So pure moment is not one of the assumptions that we make. If you do, then none of this would be possible. Everything would be identically zero.
Okay, so besides that one, I made this way too small, I'm sorry. Here, the max occurs at where the minimum of the yield stress is, which is oftentimes the outermost edge. I mean, not the outermost edge, it's the point where the flange and the web join together. So this can be done. I found this online in a textbook. I know it wasn't really covered in class, but it helped serve the purpose of this problem really well using the shear flow. So the shear flow was defined as the shear stress over the moment, and using a little bit of manipulation, we can get it and then along with the I's, which are not the moment of inertia, those are, I guess it's supposed to be J.
Just clarify that the shear flow is not the shear stress by the moment, it's the shear stress times the thickness. So whatever is the thickness through which that is happening, so it's essentially, so for example, if you have a shear stress of this, so essentially that shear stress times the thickness is like as if shear were a fluid and it was flowing through that. Or what if we have the shear stress in this direction over here? It's that shear stress multiplied by this thickness, so essentially gives you a shear flow over there. So it has nothing to do with the moments.
Okay, so then this term is misplaced. This should be over here. This is the thickness. Yeah, after that, I just did the first moment, which we looked at, which is J, but I wrote it as I. And going down, we can find that the max flange occurs at the edge, furthest from the centroid. And looking through, we have to find the tau max flange is there, and then the tau max web is here. And then we can go through and divide out the terms. And I more interpreted this as the ratios between the different factors that go together. So we can see that, changing the shear flow in one of the parts, how that will affect the other one, and how that will affect the overall tau max flange and tau max web. But all of this ultimately does depend on the cross-section geometry. So changing the different sizes will change the different thicknesses and give you different results.
We're not getting anywhere close to what we want over here. It's just that we have to have the appropriate, so like what I was describing to him, Aryak, in terms of the shear stress, how you determine the shear stress at different location. I think on the second slide that he presented, he had those pictures and he was trying to get to the expressions for the stresses and strains. So whether you use shear flow or not, you will still be able to get to that. Using shear flow makes it a little more elegant and simpler, but shear flow is nothing but shear stress times the thickness, so you can always do it with just the shear stress times the thickness itself. But at the end of the day, this is something that will be purely a geometric result. It has nothing to do with the actual shear flows that you have. Okay? So all of that has to be expressed in terms of the geometry, in terms of the material parameters, in terms of the load that is happening by B. And then eventually most of those things will cancel out and you'll just get a ratio, just like what he got for the tau max versus sigma max, a function of the A's and B's of the major and minor axis of the beam cross section. So something similar to that you will get in terms of your D, H, and thicknesses of the two quantities, the flange thickness and the web thickness. Okay. So just try to revisit that and see for yourself.
So
You also have a present surprise. Okay, I'm always jumping in. Right, okay, go ahead.
so this one is just for the shear, not the shear, the stress, sigma of max web over max flange.
The normal stress.
Yeah, the normal
so
stress.
So here, what you're saying is right, the assumption that it's subjected to pure bending again.
Yeah, I copied the same diagram over, so I think I just forgot to take that one out. Yeah, so this one was a little bit simpler than the other one because it didn't require the use of shear flow. It just had to be used from the same property that was listed before, where it has to be measured from the distance of the neutral axis to the edges, which is used to find the centroid. So we can find that these terms will ultimately lead to the max flange terms, which I have as as dependent on the moment. I forgot what C was. I'm sorry.
Yeah, again, see the eyes that are involved for any cross section cannot be the parts of it. It is eye for the entire cross section, the flange and the web put together. Okay. So you will not have something like this. You will have something coming The reason why they are different is because of the way in which the shear stress, the axial stress, the bending normal stress will get distributed. So for just a pure rectangular cross section, we already saw that it was linear, right? So this is nothing but two rectangular cross sections put next to each other. So it will be linear within each of them, and where there is a discontinuity, there will be a jump. So it's essentially piecewise linear. So that's the piecewise linear model that you would have to get to that. And based on that piecewise linear stress, then you can determine what is the maximum values, because you then plot how it's changing along the height, and then how it is changing along the height. And using those two, you can determine what's the maximum and what's the maximum in this, and then you have to just compare those two.
Okay, so when you say that I
there's
doesn't,
nothing like an eye flange or an eye web.
just nothing there?
Yeah.
Okay,
Yeah. It's eye for the whole cross section.
okay. That's it.
You done?
Yeah, that was all the corrections that we had.
All right. Thank you. Thank you so much. Any further questions you have on anything related to what you've done or structural analysis?
So,
Please ask.
I just had a specific
Yeah.
question. So when you were talking about like, the first slide, so it was just very simple, but like,
Can you go to the first slide?
like the first slide I was presenting. Yeah. So
Yeah, yeah.
this top half here, were you,
Full screen?
when you were talking about this, were you referring to tau max the entire time or sigma max?
There, yeah. So it doesn't matter. So whatever it is, when you're talking about the J, yes, the J equal to, IZ, for example, in what we call in dynamics, equal to Ix plus Iy is valid for planar cross sections. Okay. Whereas here, the polar moment of inertia doesn't play any role at all. Okay. So, but these two do play a role. So these are very important for your sigma max problem. I didn't know you had a separate slide for your tau max. I thought once you introduce the J, you're going to use this for your, which would have been wrong.
Right. Yeah. Okay.
So, did I understand your question? Or you got
Yeah,
the
yeah,
feedback?
I think so. So then, would you like me to like, sort of redo this part, I guess, or?
No, I think that's fine.
It's-
It's just that you don't need this at all over here, right?
Okay.
So
Okay.
you need only the IXs and IYs. You don't
So
need,
then the
so this
IX
is
or
wrong.
IY
Yeah,
would be
yeah,
down
yeah,
there
yeah.
instead.
The appropriate I, depending on which direction it is bending. So let's say this is the X direction,
Yeah.
and Y goes in and Z goes up. Then essentially what you're looking at is, if it's a bending this way, then it is the I about the Y axis.
Right.
If it's a bending this way, it's I about the Z axis.
Okay.
So the appropriate I would come here, not J naught.
Okay. Okay. So then that would be just
Yeah.
a simple like substitution,
Correct.
and then that would obviously affect the ratio. Okay.
That's
All
right.
right.
Yeah. So instead of that sum, you will be having only either one of them.
Okay. All right. That makes sense.
Has anybody had any questions on what you have done?